In this video, I want to introduce the idea of CPU scheduling. Scheduling is the basic problem of saying, okay, I have a bunch of processes running. How do I figure out what order I should execute them in? It's very typical, right, for an operating system to have many processes running, and we're going to have to be smart about choosing what gets to run in order to give basically some overall, good performance, right, or give the response the user wants. We'll end up kind of talking about some criteria for this, right, some background for it, and then move on to kind of a lengthy discussion of all the different algorithms we can possibly use. So the first thing I want to talk about is burst patterns. So this is kind of how a program acts. So a program is running, right? Program is running, it needs to do stuff. Typically it has what's called like a CPU burst, right? Or maybe an I/O burst, right? There's two central kinds of work a process can do, right? Either CPU or I/O. For CPU, that's basically saying that the process needs to jump on the CPU, right? Go to the die, right? Do a whole bunch of computation heavy stuff. Versus I/O, typically what that means is the process is running and maybe needs to get some data from a hard drive, right? That takes a little bit of time, right? I need to go to an external device, spin it up, whatever. But programs somehow are built around these ideas of bursts, right? So I have a CPU burst or an I/O burst. Now, a program that's basically running, right? It's going to be sitting in some sort of a queue, right? So it can be sitting in a queue to jump on the CPU. It can be sitting in a queue to go and use I/O, right? It can be one of those two places. Now, overall, right, if you think about this burst model, right? At least in terms of CPU, what happens is we get sort of this exponential distribution. So you can imagine a program is running, right? Let's take a look at the chart on the bottom right. So what this is basically frequencies of CPU bursts. The idea being is that CPUs, right, the processors running, right, as they need to use a CPU, right, they'll request some time. There's kind of a distribution to how much they request. So this diagram here basically is duration at the bottom and frequency on the side. And so if you look at this, what you can see is that there's kind of this trend. So things that are super low duration, right, there's not that many of them, right? But as kind of the duration goes up, kind of the frequency goes up as well, right? So I go up, and somewhere around here, right? I don't know. This is maybe say 2 milliseconds, something like that. That's kind of what the most frequent thing is, right? And then there's a fall off, right? So all of a sudden, things become less and less. You kind of move down, and eventually, right around 8 milliseconds, right? This is basically kind of a cutoff, right, where all of a sudden there's not really going to be many requests that are made of that size. So this is just kind of an overview, right? This is kind of an idea, I guess, of what should these CPU bursts look like. And it's going to be important for us, although not quite yet. Some of the idea is that if we wanted to make sure that processors are allowed to do what they want to do, we should give them this much time, right? We want to give them 8 milliseconds. If we do that, that means that basically processors will be able to complete their CPU bursts whenever they actually happen. We don't need to worry about giving processors this huge amount of time every time they run, because, oh, hey, there's not going to be a whole lot of processes over here, right, that require 16, 24, 32 milliseconds. As long as we have our scheduling right in terms of these shorter jobs, then we should be good to go. Okay, now if you think back to kind of our earlier discussion on processes way back quite a few units ago, there's kind of this idea, right, that all my processes are going to be waiting throughout different queues. And so we had basically this idea, right, is I had something like a CPU queue, right? We had basically something like looks like this, right? There's some sort of a ready queue, right? Ready queue goes to a CPU. Let's call this ready queue, CPU, right? And then maybe the CPU things basically can filter into some sort of an I/O queue, right? All the rectangles are representing queues. Put in some arrows there just so we know what's going where. So you have I/O over here, right? Maybe this is I/O. This is another type of I/O. Could be a bunch of things. But there's this overall, right, there's this queue system that's going on. And so my processes basically sit around in the ready queue, right? Then they go do some CPU stuff, right? And then they go into the I/O queue, right? And they're going to be waiting there, right? That's kind of when they're in a waiting state while they're waiting for some resource, right? And then once they get that resource, they can basically return to the ready queue because they need to have CPU time or actually analyze whatever it is they loaded up. Overall, our job is to find some sort of algorithm that can look at that ready queue and pick what is the best or most appropriate process to pick out of it and give it CPU time. An alternative name for this problem is the interval scheduling problem. So there are 4 different times that we may have a change in the process that's currently running. And they're listed up here on the slides. So first of all, when a process switches from a running state to the waiting state. So this is basically saying I have a program that was running. Maybe they made an I/O request, and the I/O request caused them, right, to need to wait and basically queue up for use of that I/O device. Okay, so that's one thing that may cause a change in the running program. Obviously, if that happens, I need to pick out something new and run it on the CPU. Number 2, when a process switches from the running state to the ready state. So basically, right, this is kind of an instance where the program is running, and maybe I need somebody else to run there to do whatever they want to do, right? I basically need to make things take turns. And so I may take a process that's running, right, and basically move it back to the ready state. So I'm moving back into that ready queue just because I want somebody else to run. It's not that the process that's currently on there, is done or is waiting for something. It's just that I've given it enough time, somebody else should be allowed to go. Third thing over here, when a process switches from the waiting state to the ready state. So what this is basically saying, right, is I had a process, right, that was queued up on some I/O device. Maybe it actually satisfied its request, right? That hard drive got back to it, it has its data, now it wants to do some other stuff. So then, right, I need to basically, move it, from that waiting for on I/O back to the ready queue, right, meaning that it needs CPU time. Last one here, right, is when a process terminates. Obviously, if a process is running, right, and all of a sudden you just terminate it, well, we need something to take its place, right? We need something to bring up something. So these are kind of the overall 4 cases we need to basically worry about, right, when processes might kind of change places. And some of these, right, basically are for a preemptive model versus a non-preemptive model. The idea there is that we may or may not be allowed to interrupt programs while they run. So when we say something's preemptive, right, what we're saying is that I can pull off a process whenever I want. So for example, the main preemptive one here is basically number 2. So running to ready, right? Basically that process is running, all of a sudden we're saying, oh, we're going to take it off, right? We're preempting it. Over here, right, this 4th one is also preemption, right? So that's basically saying, oh, hey, the process is running, I'm just going to kill it, right, and start something else instead. Again, we're preempting it, right? We're not letting it finish. Right? We're not letting it just do whatever it wants to do. So yeah, there's kind of these 2 basic kind of categories here, right? These are the ones that all of them happen, right, in a preemptive system. Only those 2 of them happen in a non-preemptive system.